Okay, so today we're going to be looking at thin layer chromatography, which is very similar to another type of chromatography that you would have already definitely looked at, which is paper chromatography. Quite a lot of the terminology and the principles behind it are similar, so we're just going to build on that and explain basically what this is and why it's used. Now, hopefully by now you will have done your first part of your aspirin practical, so you should have made aspirin either the green chemistry route using the microwave or the other route using the concentrated sulfuric acid. Um, and hopefully you've got some aspirin that we're now going to test in the next lesson using thin layer chromatography. So we're basically going to test the purity of it. Okay, so questions as usual. This one shouldn't be too long. This video should be quite short. So we've got 3 questions there, which you can obviously read through and get in your mind so that we're ready to go. So the first thing we really want to do is define what we mean by chromatography. So chromatography is an analytical technique, but there are different types of it. Okay, so there's not just one type of chromatography. There's different types that we will look at. But today we're just looking at the one. So we're looking at the thin layer chromatography. Now, all chromatography involves a mobile phase and a stationary phase, and it basically involves um, adding a sample, your mixture of compounds, into these phases and seeing their relative affinity for either of these phases. So how likely they are to bond with either the mobile phase that's going to move, obviously, or a stationary phase that's going to stay where it is. And like I said, there are different types. We're only going to look at thin layer chromatography today, but you will look at another type in the future. So what I'd like you to do is, using your ideas textbook, you're probably going to need to use the index, and you can find the chromatography section. So I would like you to identify what the mobile phase and what the stationary phases are for thin layer chromatography. So you'll need to pause here, just have a look through your textbook and just make notes. What's the mobile phase and what's the stationary phase in thin layer chromatography? Okay, so hopefully you will have found that relatively quickly and you've got some notes now. So essentially what we have is we've got our beaker, okay, and we have our TLC plate, okay, and a TLC plate is basically it's a metal sheet and it has a very thin layer of silica gel on it, okay, and that's the stationary phase. And then we have in our beaker we have a thin a small volume of solvent, okay, that will actually travel up via capillary action. It will travel up our TLC plate and hopefully drag the compounds with it. We also need to have a lid, okay, just to stop the evaporation of our solvent, okay. And essentially what we're going to do is we will leave it like this, and we need to ensure that the solvent is lower than our initial sample spot, because otherwise the sample spot will actually just bleed into the solvent phase, and it will just be in the solvent there in the beaker. So we need to make sure that the level of the solvent is lower than our initial spot, and we also need to draw this line here, the starting line, and that needs to be done in pencil. Obviously, for obvious reasons, inks will separate, so we need to do that in pencil. And what we should see is, after a period of time, our solvent will have moved up, okay, and this is called the solvent front. So that's basically the level that the solvent got to. And when it gets to about here, we'll actually take the TLC plate out. So once it gets close to the top, we take the TLC plate out and we can leave it to dry. And what we would hopefully see is the different compounds, okay, separated into separate spots. So our initial mixture spot has now separated into 2 or more different spots that represent each compound within that mixture, okay. And the position of these spots tells us quite a lot about these compounds. So the question really is, why does one spot move up higher? So why is one spot higher or closer to the solvent front than the other one? So why is B lower down? Okay, and why I'm saying higher up the stationary phase, just because we're referring to this silica gel as our stationary phase. So why does it move further through the stationary phase than the other one? Okay, so use your textbook, see if you can come up with an answer to this. I'll give you a bit of time and then we'll go through it. So the real reason, okay, the sort of simplified was just sort of the reason is that compound A, whatever it may be, has a higher affinity for the mobile phase than the stationary phase. And what I mean by that is it's more attracted, okay, to the solvent than it is to the stationary phase, to the silica gel. So it's traveling with the solvent further than than B. So compound B has a higher affinity for the stationary phase than the mobile phase. So it's actually bonding itself to the silica gel more than it is with the solvent. So the higher up a compound moves, or a higher up a sample moves, so the higher up the spot is essentially, the higher the affinity for the mobile phase, because it's moving with the solvent, with the mobile phase, up the TLC plate. Whereas something that stays lower down means that it's got a high affinity for the stationary phase rather than the mobile phase. And we can actually talk about this in a different sense as well. But first of all, what do we mean by affinity, and how can we change this different affinity? So in TLC, we've said that they're separated based on their relative affinity for the two phases, either the mobile phase or the stationary phase. But what can we do to affect that affinity? Well, there are three things, okay? So the polarity and the size of the molecule, we can't really change that, because that's just the sample it's the molecule we're sampling. It's there. We can't really change that, because that's what we're trying to analyze. So the polarity and the size will affect its affinity, but we can change the polarity of the stationary phase and the polarity of the solvent, so the mobile phase. And by changing those things, we can change how these compounds will separate. Okay, by changing the polarity of each of these, we can affect how they will separate. And why would we want to do that? So some of you may have sort of thought, well, if it's about affinity to the stationary phase and the mobile phase, then why do we not just have a spot right, at the bottom, because it's got a high affinity for the stationary phase, so it's just going to stay where it is, and the other one's got a high affinity for the mobile phase? Well, should move all the way up. Why doesn't it move all the way to the top where the solvent front is? And the reason for that is because it's not just a straight, this has a high affinity for this has a high affinity for that. It's actually about an equilibrium. Okay, so the relative affinities of these compounds to the different phases, we can describe it as an equilibrium. So say we were looking at A, and A moved far up our TLC plate, which means that it had a high affinity for the mobile phase. What that means is the equilibrium, so it's in equilibrium between the stationary phase and the mobile phase, but the position of the equilibrium for A is in the mobile phase. Okay, it's not only bonded to the mobile phase, but the vast majority, okay, the position of equilibrium is into that mobile phase. So the vast majority of those particles will be in the mobile phase. And the opposite is true then for particle B, so compound B. That has a higher affinity for the stationary phase, which basically means that the position of equilibrium for B is into the stationary phase. So the position of that equilibrium is in stationary phase, which means that there are more of the B compound particles attached to the stationary phase than there are to the mobile phase. And we can look at that in terms of some arrows as well. So A in the mobile phase and A in the stationary phase, we can see here that the position of equilibrium for A is into this mobile phase, depicted by this sort of red arrow pointing this way. So that's much larger, which means that the position of equilibrium for A is in the mobile phase, which means it's more likely to be found there. Okay, but we can change these equilibrium by changing the affinity of, the polarity of the stationary phase and the mobile phase. So we can change where this position of equilibrium lies. And then we've got B, so we've got the stationary phase and the mobile phase, and we can see that the position of equilibrium for B is in the stationary phase. So this arrow is much bigger. It's saying that more of the particles of B are in the stationary phase than are in the mobile phase. But that doesn't mean they're all in the stationary phase. It just means that there's a higher proportion of them in the stationary phase. Okay, so that means it will move up slightly because it will have some affinity. Some of the particles will have some affinity for the mobile phase, so it has moved up, but the majority of them are in the stationary phase, so eventually it's not going to move up as high. So it's good to think about this in terms of an equilibrium, that both A and B are not just in one of the phases. They're in an equilibrium between the two, but the position of equilibrium determines where they're, how far up they'll move. So A got higher affinity for the mobile phase, which means the position of equilibrium is in the mobile phase, and the opposite is then true for B. So how can we determine how far up something's moved? By, it seems quite qualitative at the moment. Oh, this dot, this spot moved up quite a lot and this one didn't. Well, we can actually calculate a value that allows us to compare how far some unknown compound has moved and compare it with a known value. So what we do is we measure the distance that the spot moved from our baseline, from the line that we started, and we compare it to how far the solvent moved. Okay, so we call this an RF value, and we can calculate it. So the RF value for A would be A, okay, so the little a, the distance of this, divided by the distance of x, so how far the solvent moved. So in this case, it would be whatever distance this is divided by 3 centimeters, and that would give us the RF value for A. So what I'd like you to do is just calculate the RF value for B. Okay, so we've got the distance that B moved, which is 2.3, and we've got the distance that the solvent moved, which was 3. So using this formula here, or the similar version of this formula, but for B, see if you can calculate that. So nice and simple. All it is 2.3, so the distance that B moved, divided by 3, which is the distance the solvent moved, and gives us 0.77. It will always be less than 1, okay? It will always be a decimal less than 1 because obviously if it moved all the way up with the solvent, it would be 3 divided by 3, which is 1. So it's basically a fraction of 1. So it's like a percentage. So this moved up basically 77% of the way up, whereas A is obviously going to be a lower number than that. So it allows us to compare how far a particular compound will move with the mobile phase. And we can actually compare these values to known values to allow us to get a bit more information. So the last thing then is just about how do we locate these spots. Sometimes if we're not using colored compounds, so if we're not separating an ink and we're not using something that's colored, then we need something to locate it. So we call that a locating agent. And ninhydrin is a chemical that's used to locate amino acids. So if we've got a mixture of amino acids and we're separating them, we can spray it with ninhydrin and dry it with a hairdryer or whatever, and the spot should show up purple. So that allows us to then calculate those RF values. And then that all works fine. But if it's not an amino acid mixture, then we can either use iodine or a UV lamp, either of those depending on which samples you're using. But iodine or a UV lamp will actually locate those spots as well. So hopefully that all made sense. That was quite a quick one. So going through the questions then, can you describe the process of thin layer chromatography, including the reason for the separation of compounds? What is an RF value and how is it calculated? And then how are the compounds located and identified on the TLC plate? So I'll let you just see if we can answer those and then we'll go through them. Okay, so we have a mobile phase, which will be the solvent, and a stationary phase, which is the silica gel. And what we do is we get a sample of our mixture and we put a dot of that on our baseline that we did with pencil, we drew with pencil, and then the solvent will move up the TLC plate, taking the compounds with it. And basically, the higher up the spot, the higher the affinity of the compound to the mobile phase, and the lower down the spot, the higher the affinity of the compound to the stationary phase. So an RF value is basically it's quantitative data, so it allows us to compare how far or how high the affinity of different compounds to the mobile phase. So the higher the RF value, the higher the affinity for the mobile phase, and it's calculated by RF is equal to the distance traveled by the compound divided by the distance traveled by the solvent. And that will be in centimeters or whatever, but RF obviously has no units because you're dividing one by the other, so it will be unitless. How are the compounds located? Well, for amino acid mixtures, we use ninhydrin and then dry that and it will show up purple. And then for other things, we can use iodine or UV light. And then we can use that RF value to compare known compounds to identify the unknowns. So we can, look at the RF value for our unknown and see if we can compare it to any known compounds to see if we can get any matches there. Anyway, so I hope that was clear and I didn't go through any of that too quickly. Remember, if you've got any questions or anything wasn't 100% clear, write them down to ask your teacher, or by all means Moodle me. I'm absolutely happy for that to be the case, or even come and see any of us at break or lunchtime if there's anything desperate you want to ask. And so I'll leave you with that. Hope the aspirin practical or the second part of the aspirin practical goes well, and I'll see you next time.